Okay, do you hear me?
Yep.
All right, and recording is started?
Yeah. Yep.
All right, so let's get started. So, signature constraints is actually not a very complicated thing. I'm just going to contradict Richard right there. But what is really complicated is the stuff that it enables and the reason why people really want it, which is rolling upgrades. And you can't really divorce the two because there would be no point in signature constraints if we did not want a better upgrade story. So I'm going to cover the slightly wider topic today as well. Okay, so we're going to talk about what are rolling upgrades and how will they work in Corda. Then we're going to discuss signature constraints. Then we're going to cover what's working in 4.0 and what's targeted for future releases. And then we're going to talk about package namespace ownership and what that is and why it's there as well. All right? Okay. So rolling upgrades, I'm sure most of you know this already, but just for people who have never worked on distributed systems before, rolling upgrade is where you have many servers doing things or many computers doing things, and you want to upgrade them all to version 2 from version 1, but you can't do it simultaneously, either because they're not all controlled by you or because they are, but you don't want to take the service offline. And this typically crops up on the web, where browsers can't handle node outages of any kind. Basically, if a web server is offline, then the user gets an error. So to do any kind of upgrade, you need multiple web servers, and you need to spray traffic across them and then roll them from version 1 to version 2. And during this time, this is a really complicated thing, because during this time, new and old versions of the software coexist, and it's very easy for this to go wrong. When working on new features, developers have to remember that old software may have to interact with software that's effectively from the future, right? It's creating data that wasn't known about at the time version 1 was made. It's changing protocols and things potentially in ways that were not anticipated, and yet the old software must be able to work and continue working. Moreover, what makes it even more complicated is if you have a partial rollout that then rolls back. So you go from version 2 back to running version 1 because you find a flaw, for example. So this process of doing rolling upgrades back and forth is very complicated, and unfortunately, and if you look at the history of outages in the IT sector, then making computer systems that are reliable when you're not touching them is actually quite straightforward. It's a well-known thing. Almost all outages are caused by attempts to change the system. So in Corda, we have a fractal problem, actually, because not only must Corda nodes be able to roll out in a rolling upgrade setup, but also applications that run on top of it. And therefore, it's not enough for us to solve this problem for ourselves. We've got to solve it for our developers as well. The alternative is that you don't do a rolling upgrade. Instead, you suspend the system. For example, over a weekend, everyone upgrades together, or all the machines are upgraded, all the servers are upgraded, and then you test it, and then you carry on Monday. That simplifies things a lot because the system is not live while the upgrade takes place. And sometimes, especially in some industries, that's expected, and you can get away from it. You can get away with it, rather, but in many industries, it's no longer considered acceptable. You want 24/7 operation. So here's the current state of play. Today we launched Corda 4.0 and rolling upgrades for both Corda and apps, mostly but not entirely supported in Corda 4.0. There are a few little bits and pieces that will follow in 4.x releases. You know, we just had to get 4.0 out the door, so there are a few details that can be fixed in follow-up releases. We had to do all the ones that affect the core data model and protocols in 4.0, but we couldn't. A few things could be left. And the goal is that, it'll take a bit of time to get this right because it is a complex thing, but by the end of the 4.x cycle, they should be working well and you should be able to do them quite straightforwardly for both Corda and apps. Now, that said, without a doubt, there will be disasters and outages because this is just such a common cause of problems in the software business. In particular, apps must be designed for rolling upgrade in a decentralized system, which is something that many of our users will not have ever had to write before, either because they've never worked on very large-scale websites or they've never worked on distributed software at all. And then the fact that this is not even distributed software, this is decentralized software, so there could be attackers in it, complicates things still further. And of course, not only app developers must think about this, but node operators must also learn how to do it safely, and we'll talk about what that means later. So yeah, if you can design things such as you have maintenance hours, then That's a recommendation we should be willing to make, for not every kind of application needs 24/7 operation, and it does have a cost and risk. Okay, so what's needed to make this work? Well, the eponymous signature constraints that we hear so much about, but that's not by itself enough. It's really helpful if you can turn your node off, upgrade it, and then turn it back on again, which means that you really want networking stacks and protocols that can tolerate like nodes going away and coming back. You don't have to do things that way. Like I said, the web doesn't have that support, which is why you end up with load balancers and DNS balancing, and it's incredibly convoluted to make the web highly available because web browsers don't retry in case of errors. They can't handle a server that's temporarily gone. Web apps don't work offline. But in Corda, we did design things so that if a node goes away, then other nodes will just pause and wait for it to come back, and you can restart your node to do things to it without creating errors at the other side. Again, that requires app developers to cooperate, and not all of them do because we don't always help explain how to do that, and we don't always provide everything they need yet, but that will come. You need two-phase rollouts of new features. We'll get to that a bit later. And then finally, you do need good communication with all the parties who are upgrading. You probably need some way to monitor what they're doing. So if they're not if they're not doing what they're supposed to at any particular point in the upgrade process, you find out and you can talk to them and help them get it right. And all this stuff currently is punted to the users, but in future versions of the platform, I'm sure this is a common need that will come up again and again, some sort of like monitoring of what's going on in your business network and the users of your apps so you can coordinate them. And today, when I say coordinate, what I mean is like emailing them is fine. Okay, so signature constraints. What is a distributed ledger? This is going to sound a little bit basic or condescending given what we do, but I'm going to go over it anyway just so we're super clear. But a blockchain is a kind of a database. It's a ledger made up of both data and code simultaneously. So it's not just data, like in beginner's sort of my first database. It's more like the combination of database tables and stored procedures. In the first generation, we had Bitcoin, where the code was this like tiny little inline assembly language that in theory was quite powerful, and then shortly after release, Satoshi realized he had like screwed it up and made a lot of mistakes. So he basically switched off most of that scripting language, as he called it. And unfortunately, it never really recovered. So it's not useful for very much, but it established the concept that on a blockchain system, you have code and data living in the same database. And then the data was, of course, the value fields in transactions. You could only store values, which resulted in lots of weird hacks, like people encoding data into the prices in a transaction and stuff. So second generation was Ethereum, in which they decided the code is a sort of stateful object in the object-oriented programming sense, and the data is like every object. What they call a smart contract is a stateful object, has like a key value store associated with it. So code and data are tightly bound together in the way that you would expect in object-oriented programming. Well, close to what you would expect. And then, I don't know if the Ethereum guys would agree with this, but hey, I wrote these slides, so I can call Corda third-gen system. Which is where we go back to the Bitcoin's data model but upgraded. So the code is sort of little bytecode language again, like in Bitcoin, but it's Java bytecode. And we don't inline it into the transaction. We don't not every transaction contains a complete copy of every bit of code. We have this notion of attachments where the transaction refers to a bit of code by hash, and then that means you can have much bigger programs and they're not copied around constantly over and over again. And then for data, it's fixed. Like in Bitcoin, once put on the ledger, it stays, it's immutable. And we allow arbitrary serialized object graphs, or near arbitrary. So the key thing is that we have this separation of code and data. So what are constraints? Well, both Bitcoin and Ethereum have a very, very hard link between the code and the data. Basically, when you put things on the ledger, you upload your code and you upload your data. And then after that, the code can't be changed, and the data can't really be divorced from the code. So that means, by implication, there's no such thing as upgrading code in Bitcoin or Ethereum by design, which is partly because upgrades are mind-blowingly difficult in any kind of distributed system, and they're afraid of it. I know they're afraid of it because I used to work in that Bitcoin community, and we were all terrified of upgrades because we knew how easy it was to break things. And it's partly a philosophical thing. They turned this weakness into a strength by talking about code as law, or a perceived strength as they saw it. So they said, well, this is how you've got total certainty that people can't screw you. The code can't be upgraded. So if you read it, then it will stay with what you read. Now on Corda, we don't expect people to write perfect code. We don't really invest in things like really crazy advanced programming languages or anything like that. We sort of expect that people will make mistakes, and we expect that business requirements will change, and therefore that both data and code will need to change, so we invest heavily in upgrades instead. And in Corda, data states is linked to code in a vague way, not a hard way. Or I should say it can be linked in a vague way. So when you create data on the ledger, you can specify that the code that is going to be used with that data can change according to certain rules. Now, the simplest rule is actually that it may not change. This is called a hash constraint, and that's Bitcoin and Ethereum style. Once created, it can never be changed. That exists partly to make us seem more blockchainy a little bit, partly because it was easy to implement, and partly because we can imagine in a big future network where some applications are just so critical to the economy, like a cash app, for example, that the whole notion of upgrading it is just nonsense, and you could never get enough agreement, and people would always worry. So we just don't allow upgrades in that case, or we say the user can select that they don't want to allow upgrades. Then we have this code that's whitelisted by the zone operator, and that was added in Corda 3 as a quick way to enable upgrades, because a lot of early Corda deployments are in private business networks. And then in Corda 4, we've added signature constraints, which is this one. And what it says is that the code you can use with the data must be signed, digitally signed, and by a threshold of keys. And what that means is you can specify, for example, that you can specify 5 public keys and say any 3 of them can satisfy this thing. So in this way, you can say things like the code must be signed by the company that wrote it, and a regulator, and maybe my business network as well, and maybe a few other companies. And so if some of those companies go bust, or they're not around anymore, or they're just not responsive at the time you want to do an upgrade, it's okay. A few can drop out, and the rest can continue without them. You can actually specify more complex policies than that, because we allow any arbitrary composite key to be used, but that's the idea. So you can have social constraints, in effect. Instead of saying what the code should do in a mechanical way, you say it in a social way. You say that this data can be used with any code that pleases or satisfies this group of people. Okay, so why signature constraints? Well, it allows you to do upgrades with a variety of nice attributes. And I should note at this point that competing platforms to Corda don't have anything like this. They either don't allow upgrades at all, as I mentioned, or they only allow what we call explicit constraints, which is where for every bit of data, everyone involved in that bit of data has to shake hands simultaneously, and then you can upgrade that bit of data. But if you have 1 million bits of data on the ledger, you have to do it 1 million times, which doesn't really work. It doesn't scale very well. So the idea is you can change the code being used to, you can change the smart contract logic that governs a bit of data on a per state basis, and only when a node is ready for the new code. There's no global synchronization like there is in something like Fabric. And you don't need any additional upgrade transactions. And that's useful because if you did, then you might get into a situation where, for example, you have 1,000 transactions per second of capacity, and at peak times you're doing 950, and therefore the upgrade process would actually never really be able to complete, because maybe people are creating new states on the old version faster than you can actually upgrade them given your capacity limits. We don't want that kind of deadlock in design, so we allow you to change code and upgrade when you need it and not creating new transaction types. And yes, like I said, you can express your desired upgrade route socially. And that's useful for tolerating things like bankruptcy or outages. Okay, so how do you use them? Well, this is really a developer feature. So you create a key pair, private key and a public key. And yes, HSMs are supported. We didn't actually have to do any work to support that because we're using the standard Java code signing infrastructure, and that supports HSMs, so we kind of get this for free. And then what you do is you create your jar, which is the zip file that contains your code, of course, and Java comes with a single jar signer, and you just use it. So we didn't have to build any of that infrastructure. We just point people at the Java docs, and they learn how to do it from the standard documentation you get from Oracle. But you don't have to do it by hand. We provide a little integration, Gradle, so that you can automatically sign new versions easily via our Gradle plugin that we provide. So we provide a bit of convenient stuff that developers can integrate and use it. And that's it. There's no step 4. So, and obviously you only create the key pair once. So really, to sign a new version of your app, you just build it and you run the tool. and then you have a signed version of your app that you can release to your users. This works because Transaction Builder, which is the bit of code in Corda that builds transactions, as the name implies, will look at, when you add a state to a transaction, it will look at the jar that contains the state using reflection and look at who signed it, and then it will assume that the state should be governed by those keys. So if your jar was signed by 3 different organizations, it assumes all 3 must be present for every new version of the app. Now, if you want to tolerate bankruptcies and outages and things, you can write a bit of extra code to tell Transaction Builder that by default it will assume everyone who signs the original app must sign every upgrade. So it sort of defaults to safety rather than robustness, I guess. Now, by itself, that stuff wasn't actually too challenging to implement. And if that's all we had added, then Corda 4 probably would have shipped at the end of the year. Well, I suppose a few things would still have delayed it, but it would have been in sometime in January. Where we really started hitting problems is when we looked at how do you migrate people from the other constraint types if they're already live. Now, in theory, this should never be a problem because we added the whitelist, the zone constraints in Corda 3, and we told everyone to use them. And we set things up as much as we could so they would be used automatically. But, well, guess what? Some people don't read the user guide, and some people have launched with hash constraints because that's sort of the one that doesn't require any setup or any action, right? Like any jar file can be hashed. So if there are no signatures and no zone whitelist entries, then the only kind of constraint you can use is the hash constraint, or we have one called always accept, which basically disables ledger security completely, and that's fine for testing and things. But on a real system, you really want some kind of security, because if you didn't have that, then anyone you traded with, or really anyone, could just take a bit of data, totally change all of the smart contract logic that governs it, and then edit it in any way they saw fit. So they could do things like print money out of thin air, which we don't want. So what have we done in Corda 4? Well, we tried several approaches, and I wrote up a big email to Corda Dev that went into why these different approaches didn't pan out. And what we're doing instead now is something very simple, which is we've added a config file option to just disable the checking of hash constraints entirely. This isn't really meant to be something you do in a consensus system, because some people might set it and other people might not, and then you would get loss of consensus. But we think that hash constraints are probably being used by accident in totally private networks where it's very easy to coordinate changes to all of the nodes because, for example, maybe they're all being run by the same company. That is a configuration that we see sometimes. By the way, I should mention why we see that. A lot of companies start out by designing a decentralized system, but then they aren't, it takes time to convince all their customers that decentralization has benefits and they want to be decentralized. So they start out by saying, we'll host people's nodes for them, and then they have optionality about whether they take over their nodes and change their private keys and things later. So that's why we end up like that. And that's why this approach will probably be sufficient in the end, even though it kind of violates the rules of what you're supposed to do on blockchains, because in practice, people will be able to coordinate that. In 4.1, we already have some support for this in 4.0, and we're planning to finish it in a 4.1 or maybe 4.2 release, which is migrating from the zone whitelist constraint, which is the one where your network operator, your compatibility zone operator, basically lists every version of your app that's allowed, which is simple but very centralized, and you have to loop in the zone operator for every upgrade, which you don't really want to do. But that's our current best alternative, and that's the one that's currently being deployed on the Corda network. We check actually that apps are using this correctly. So migrating from those to signature constraints is a lot more straightforward, and there will be a migration path for that that's fully automatic as well, not just existing like it does today, but fully automatically used in a future release. Okay, so let's talk a bit more about rolling upgrades. So I mentioned, it's a complicated thing. Signature constraints aren't really enough to get rolling upgrades correct, and ultimately it's this smooth upgrade process that people want. Signature constraints are just one of the building blocks. You also need data evolution rules that allow you to evolve things in a backwards compatible way. That means new software can read old data. You also want to avoid the opposite. You want to check for data loss bugs. That means you want to detect accidental forwards compatibility, and we've added that in 4, and I'll talk about that in a second. We also have this notion of whitelisting of what smart contract code you're willing to run for now. That's kind of a safety mechanism because we're still working on integrating our sandbox, like our equivalent of the Ethereum virtual machine. Our early customers don't really need it because they have a lot of control over what's happening in their systems, so it's not integrated yet. But we do have instead a kind of a whitelisting, so you have to say, I'm going to allow this new version to run on my computer. And that can be done in 4.0, but it's pretty bit awkward, and we're improving it in 4.1. And then once the actual features are in place, we're going to need to do, this is going to be a long-term ongoing project, right? Because this stuff is hard, and we're going to need to document best practices and incorporate it into training, perhaps some sort of advanced Corda training course that we're putting together. And then we need, we have some of this ourselves, but we need to productize it and get it out there to developers as well, like test frameworks to allow Corda app developers to simulate rolling upgrades so they can verify they've done their bit correctly. And this is something that will, come in over time. These sort of version numbers on the screen, of course, are guesses for the ones in the future, but that's sort of what the rough order of priority. All right, so backwards and forwards compatibility are one of the most confusing topics that make rolling upgrades hard. Most developers have heard of backwards compatibility, right? That's easy enough. That's I buy a new computer or I run a new version of my software and I can still open my old documents. And that's easy because you know what happened in the past. So as long as you remember that new data fields and new features might not always be there, and you make sure you check, then it's not too hard to get right. And Kotlin is especially helpful for this, for developers that use it, because as long as you remember when you're adding a new field to the software to mark it as optional, then Kotlin will check, of course, every time you use it to say, hey, you're just sort of expecting it to be there, but it might not be, and you need to tell me what to do. So you can't forget, which is a very common source of bugs in Java programs, for example. Forwards compatibility is trickier because then an old program is receiving data from the future, which has presumably got more stuff in it. And handling that is very difficult. You can do it in a bunch of ways. For example, you can keep it around. You can say, I don't know what this stuff is, but I'm going to keep it around and then forward it on. And that's kind of how some things inside Google work, for example, and companies like Facebook, they have servers where if they don't understand things, they kind of remember it and put it back if they send it to some other server that might understand it. Unfortunately, this works right up until anyone copies a piece of data into a new structure, which happens all the time, especially these days because people love their immutable data structures. And in particular, it happens all the time in Corda, because the blockchain is meant to be an immutable record of what happened. So you're always copying old things into new things. And it's very easy, of course, if you copy field by field and then there's one from the future you don't know what to do, well, you've got nowhere to copy it to, so it just goes missing, gets dropped. And as a consequence, it's very easy to accidentally delete data during rolling upgrade if you put data into the ledger that old versions are not equipped to handle. They'll just strip it when they edit the data. So we added in Corda 4 an anti-dataloss rule, and it says if a field appears from the future and the embedded schema that we put into our AMQP messages says that it's nullable, i.e. optional, and it's actually set to null, i.e. the slot is there but there's nothing in it, then it's okay to strip it, right? You can ignore it. You can continue because there's nothing there to delete. And that's a happy path. That's what happens when developers understand the rules and they're doing what's called a two-phase rollout, which is where in phase one, everyone upgrades to a new version of the software that understands the new features and new data fields, but doesn't actually use them yet. And then in phase two, that's when you can start using the new features, because at that point, everyone can handle it. If that goes wrong, for example, if Alice upgrades from version 1 to version 2 and Bob is still on version 1, and Alice immediately starts using the new feature and adding stuff to the state that Bob is not equipped to handle, then Bob will see a field appearing from the future, and they'll know if a new field has appeared because they'll look at the schema and say, hey, there's this new thing, and I don't know what it means. And the schema says it's optional, or its schema says it's not optional, or if it's optional but it's filled out. So basically, if it receives a message from the future and the field is there and it's got data in it, then we might risk losing the data. We don't want to delete things from the ledger if they were put in there. So we throw an exception, we refuse to accept the transaction, the flow framework unwinds everything, and Alice learns that, Bob doesn't really understand what's going on, you're not in consensus, you do not have, agreement on what I see is what you see, and the flow will, I think, go to the hospital until it's feeling better. And what that means is, the admin will see in the logs that this happened, and they can upgrade their app and continue. Is the idea there. So Alice will wait until Bob catches up with the upgrade, basically. Okay, so that's rolling upgrades. Now I'm running out of time, but this next one is a lot faster, so hopefully I can go quickly. So package namespace ownership is an unrelated feature, it's a separate thing. So the problem is this, it's about identity again, that most awesome of topics, always very enjoyable. On the internet or on a distributed ledger, you could be an attacker. You could be someone pretending to be someone you're not. Now, code in Java is, as we all know, it's split into classes, and classes are named. And in Java, there's this convention that you name things with the reverse domain name of your company or organization. So lots and lots and lots of Java code starts with com.megacorp, ours is net.corda, and then, of course, you've got this whole namespace hierarchy where you can categorize things. And that's pretty good. This is one of the reasons to use Java is because it's very organized in this way. And most languages don't do that. They don't have any notion of, this convention. So people just pick whatever name they like, and they sort of hope it's not taken. But in Java, you use a domain name system. So if someone owns com.megacorp, then they should be able to use it. And this is really important. Naming is very important, especially in large distributed systems, because that's how you know what something means. Right? If you get a piece of data and the name is wrong, you're going to misinterpret what it means. And in particular, you will misinterpret the business logic, the business semantics that led up to you getting this data. Like what makes cache cache on a distributed ledger? Well, it's because it's a bit of data that calls itself cache, and you know that anything that calls itself cache must have followed certain rules. So names matter. But the problem is that as programmers, we're pretty sloppy about it. Names tend to get lost. They often get shortened. They get mixed up with each other. People take them for granted, right? They just assume if a bit of data says that it's a thing, then it must actually have been that thing. And in Java, this sort of problem is also prevalent. We have this convention that you reverse the web address, and that's your space. But it's not enforced by anything. It's just a convention, right? And you can violate it, and I could tomorrow write and publish software that is putting stuff in like com.microsoft.whatever, and no one would notice. No one would be able to stop me. No one would even be able to say I was breaking any rules because, like I said, it's just a convention. And even if people are following the rules, who says that com.megacorp will always be owned by the same company, right? Domain names do change ownership from time to time. So this is the problem we've got. Attackers can create code with whatever fully qualified name they like. And Corda itself is not fooled by this. The core ledger in Corda thinks of code in terms of attachments and constraints like we just saw, and public keys and hashes and mathematical things that have a firm grounding and it can't be forged. But other systems don't think like that. They predate cryptography, or at least a widespread use of cryptography. And so the moment data exits the core of the Corda node, it enters this much more sort of jungle of names where things, are not necessarily what they seem. For example, our own RPC system thinks in terms of type names, right? And so the moment you receive data from a Vault query, then it will be deserialized from the wire and then mapped to whatever your app is, even if the one that was on the ledger is a totally different app, actually. And that's our format. That's the one we designed, which at least has type names in it and schemas and things. But a lot of people are using formats that don't even have them. Right? JSON is really popular. It doesn't even use type names at all. Only the shape matters. And XML, it doesn't even have the shape necessarily. So it's really hard. And then even programming languages themselves, Java and stuff, it has no notion of cryptography, right? Like all public key stuff is tacked on the side in languages like Java, and every programming language actually, they all think in terms of these names. So even if you just stick to data formats, it's not enough. You would end up getting confused when you're naming things in software. So this is a pretty subtle problem, and we thought about it a long time ago and thought about it quite deeply, and it's very easy to get confused. We thought about a lot of different solutions, like maybe we should just expose constraints everywhere. So if you get data from the ledger via RPC, we send you the data and also the constraint that it advertised, and then you can check it against your local software to check it all lines up, for example. So that's exporting Corda's notion of identity everywhere else. And we thought, well, it'd be easy to forget. And maybe we can fix things with class loader magic so that the JVM actually enforces this so you can't forget and you can't get mixed up. And eventually our heads exploded and we said, no, it's not going to work. It's too hard. People will make mistakes and glue things together, systems, legacy systems, and it's not going to work. So, different approach. Introduce a bit of optional centralization, which we don't like because every time we do that, our customers get upset at us. But in this case, we do it anyway. But it is optional at least. And the goal is to establish a tight link between this Java naming convention and the actual reality of who owns what. So package namespace ownership is a list of package names and public keys. And it's published in the compatibility zone parameters. So it's controlled by the operators of your compatibility zone, the Corda Foundation, in the case of the Corda network. The package name is a prefix. So if you claim com.megacorp, then like every package under that com.megacorp.whatever is also claimed. And when the claim appears in the network parameters, you can only define classes in that namespace if the jar is signed by that key. So the assumption here is that when you created that key back on slide 5 or whatever to use signature constraints, you sent that public key to the zone operator and said, hey, I work for a company that actually owns com.megacorp or megacorp.com. Sorry, and you can prove that by that's your email address, for example. And then they add it to this list and publish it, and now only your employees can publish stuff in this namespace. So a name will actually line up with what it actually looks like. So perception and reality will be closer. People will be less likely to get confused. You will not be able to get data coming out of the ledger with confusing names, assuming that developers play ball, and the system should be safer and more secure as a consequence. Now, there are a few things to be aware of, right? So we have this notion of a legal entity name in Corda, which is very important, but what we're talking about here is actually a brand name check, right? So a lot of financial institutions have many, many legal entities, but like one top-level domain name, and that's where they put all of their code. And it's not even necessarily a brand name. It could just be whatever website they happen to use. So verifying ownership of this can be automated in slightly different ways, like just emailing someone and checking they received the email, confirmation link. But it's actually, we must keep this distinction separate. Also, if someone claims ownership of a namespace that's already in use and there are unsigned apps out there that use it, then of course that will be detected as an attack because someone who is not signing with that identity is publishing code under that name. So you do need to get this right from day one, really, ideally, and therefore the Corda network onboarding procedure should tell people about this feature and say, hey, you should probably generate a key and send us a public part so that we can register you for this feature if you want to. Of course, if they don't want to, then okay. Why might they not want to? Well, because they're just an app publisher and they don't care what zones their apps are used in, for example. In which case, maybe it's the user doing it on their behalf or whatever. And of course, it's a bit of a privacy leak because now the zone operator is aware of what apps, or at least what app vendors are in use in their zone. And we tried hard to make sure that the zone operators are not really involved in what apps get used. We don't want them to have that power. But like I said, it is optional. So if the zone operator doesn't play ball, you can always just ignore them. And also, if you don't want them to know at all, then you can just register some top-level domain name that it's just whatever. It's a code name or whatever. And then you can use that. There's no particular reason it must actually line up to a real legal entity name or even a brand name. It just has to be a name that developers will recognize and can work with. Okay, so sorry I ran a bit over. I wrote this talk in a hurry. Are there any questions?
Hi, Mike. Thanks for the presentation. So I would like to make a question regarding the rolling upgrades. Mm-hmm. You mentioned that there won't be an upgrade transaction flow. So I was wondering what defines which version of a contract will be run. So the class of every state defines which class will be run. And I was wondering what defines which version of that class will be run. What part defines that? I guess it's the database of each node, right?
Yeah, it's the version that's currently installed in the node building the transaction. So imagine that you've got Alice and Bob, and Alice is running V2 and Bob is running V1. Then Bob will build a transaction with V1 attached to it. And therefore, if Alice has created a state and sent it to Bob, right, then it will have been created with V2, but then it will be used in a transaction that has V1 attached. That's why there's a downgrade data loss check, right? Because Alice might have put something in the new fields and doesn't want them to be lost.
Okay, I see.
We did originally, and this is one of the things that caused Corda 4 to be delayed. The original logic was slightly different. It would actually select the latest seen version, which sounds intuitive, but what that means is that once the rolling upgrade begins, it would like start to spread virally through the network because all the nodes would like download the latest version from Alice as part of verifying the transaction and then start using it themselves. And so you would have an update that goes like bang as it like business flows to the business network, which is not at all intuitive. And luckily we caught that and reset it to what it's meant to be, which is the installed version. So you can control what version of your transactions are using. You still have to execute code from the future if Alice is using a new version, because you need to check her transaction, of course, but you can use older versions.
Mike, can you give a little bit of, I guess, color or guidance on some of the gotchas people may hit? So you said something earlier, which was the transaction builder attaches your Corda app. You talked about how the Corda app needs to be signed. I'm guessing what you meant was the Corda app kernel or the contract states and dependencies. It seems that people have been playing with release candidates of Corda haven't necessarily built their apps in the right way from a modularization perspective. Their dependencies might be bigger than they should be. So any guidance on some of the most obvious things to avoid to avoid tears?
Yes. Right. So the recommendation starting from Corda 4 onwards, actually it was kind of a recommendation in 3 as well, but we weren't really following it in our own examples, so not surprisingly no one else did either, is that you split your app into 2 modules. There's the contracts jar and the workflows jar. You don't have to, in theory, but if you don't, then your flows will get copied around the network and stuff, and even though they're not being used, which is a bit inefficient. And maybe you want to have like proprietary code in there or something like that. So it's better to keep all of the code on the ledger as minimal as possible. And what we what we've been seeing sometimes is where people are putting like way too much stuff on the ledger. Basically, they're putting way too much logic on the ledger because hey, it's Java, so why not? You can just like throw code in there all day, and there's so much you can use. But it's meant to be a little bit more like Ethereum, where you have like these small kernels of logic and smart contracts that run on the ledger, and not like full-blown applications. In particular, what we've seen, with the tokens SDK, is we started to get a little bit too clever with breaking things up into modules and things, and making it super software engineered, basically. And Corda does not have all of the functionality you want to make that work really, really well. For that matter, neither does Java. A lot of these scenarios people are coming up with and saying, oh, I'm getting stuck with constraints or whatever. When I look at them, I think, well, that would actually easily cause problems even in a regular Java program, because you might get into complex dependency configurations that don't quite work. So it's really all about keeping it really simple and not trying to be too adventurous, and making sure that you understand what code is going into what modules at all times. I lost you again. Sorry, I can't hear you.
I don't have to hold
there
it down.
We go.
Yeah, sorry. Mike, could you tell us a bit more about how the centralized package namespace check works? I mean, if there's a node that wants to check if there's a node that wants to transact and it's got a package that has been signed, how would it know which server to ask if the package has been signed with the right key?
Mm-hmm. Yeah. So the list of ownerships that I mentioned as a part of what are called the network parameters. They should really be called the zone parameters. Unfortunately, we didn't really fully execute that renaming when we did it. But essentially, every Corda node is joined to exactly one compatibility zone. And the way that's implemented is you point it at a file, basically, on a web server. And it's a static file that changes occasionally, and the nodes poll it. And it's digitally signed by the public key of the node of the zone operator. So for most deployments, we hope that that will be the Corda foundation, because we're trying to build a global network, but it doesn't have to be, of course. You can run your own zone. And the operators of that zone decide what goes in that file. So you contact them and they publish this new linkage and they update the file in the web server and the nodes download it. And also what we added in Corda 4 is attachment of the zone parameters that were in force at the time the transaction was built. So for any transaction, you can look and find out what the parameters were at the time that transaction was made, and therefore, by following all the links all the way through, you can see who owned what at that time and check they match.
Hey, Mike, Austin here. Another question on the PNO stuff. So it's since that's in the network parameters, every time someone claims one of the namespaces, that's going to require a flag day across the whole network?
No, something that's no, so in Corda 4 we've added this notion of auto accept changes, and for certain types of change, they are accepted automatically by the node without needing a restart or a flag day or any kind of acceptance process, because the assumption is that they will never be controversial, basically. Also, because those certain sorts of changes, like adding things to a list, can be done in a thread-safe manner without complex synchronization inside the node. So whitelist entries and also package namespace ownerships can be added to without a flag day in 4. Okay, any other questions?
Hi, I got one quick question. So under this new model, Corda app developers have to manage their own private keys, right? How much rigor do we expect them to manage those keys with? And could it be a problem if they don't manage it with sufficient rigor?
Yes, it could be. So the question is, what can an app developer do with a stolen private key? So what they can do is, publish new versions of the app signed by that developer. Now, today that wouldn't help you very much, because you would also have to know the customer list and get in touch with your users, and there's no automated infrastructure for that, right? But in future, if we move to a model, and we probably will, because we want Corda to be usable by small companies and maybe one day even individuals, which is more like an app store kind of model, where there's an automated distribution and automated propagation of updates, then losing your private key is a very serious thing indeed. Now, this is a very common approach. So Android and iOS and Windows and macOS all use code signing. And if you want to publish apps to these platforms, you need to generate a private key and get it approved by certificate authorities, and then you can make apps. And even then, Windows, merely signing the app is not even really helping you get past all the security warnings on Windows, because they use it to calculate a reputation. So if you're a new developer, you have to get your early users to plow through these horrible warnings that say, don't touch this, it might be a virus. And then after you succeed in running that gauntlet, then Windows learns that, hey, people install this app and they don't uninstall it and they don't complain. So it's probably not a virus. And then the new versions of your app don't have to go through that again, because they're signed by the same key. So Windows code signing requires keys to be held in an HSM, basically, these days, or at least a smart card reader. That's a bit of a pain. I've been through this before. I have a current Windows signing key, and it's actually in an HSM in the cloud. So the certificate authority itself has generated the private key, and then I use two-factor authentication to trigger signing, which is not really how private keys are meant to work, but it meets Microsoft's new security requirements, and means I don't have to faff about with the local smart cards and things. And it's probably just as secure, because we already assume the CA is itself secure. So if the CA is hacked, then it doesn't matter if you keep your own private key safe. And we'll probably use the same kind of approaches there.
Okay, cool, thanks.
The point is that because we're using the standard Java code signing infrastructure, which has been around a long time, we get all of that for free.
Any more questions? If there are no more questions, I think we can wrap up. We'll run over a bit. Thanks, Mike.
Thank you, and sorry for you, everyone. Have a nice afternoon.
Thank you.